And our speaker will be Ignacio Becker, Scalable end-to-end recurrent neural network for variable star classification.
Thank you. Hello, my name is Ignacio. I am a computer science PhD student at the Universidad Católica in Chile, Santiago. So the title of my presentation is a mouthful, but we can go it, we will do it piece by piece. So the main motivation of my work is that we are in a tsunami of data, right?
Scary.
But that's not it. This is the picture. So we have to be able to do it all day, all the time for 10 or more years. So this is quite a challenge. And so we need help. And the problem is even worse because we have this taxonomy that is even weirder, as we know for the previous talks. So what can we do? It's really hard. So we have classes and subclasses of objects, transients, asteroids, and many things. But let's go piece by piece, right? So my work is in ALERCE, which is the automatic learning of rapid classification of events, which is the broker led by the Chilean community. So yeah, that is competition. So we want to classify everything. That's the idea, right? So we are building more telescopes. We are designing more surveys for extending previous ones. And we have more data than ever, and we can ask more questions, right? But that's a problem because we have to start somewhere. And you see a cepheid here, which is really pretty, but the data will always be ugly, right? If we are working with pretty light curves, we are doing the science wrong because we have to go deeper. We have to go to the limit. We cannot keep working on pretty light curves all the time. So this is not the case. So forget that. So we have machine learning tools that will help us to do our science. So first, they are tools, and we can use it wherever we like, but and they are as good as the training sets. So if we train them with really pretty data, they will work on pretty data. That's it, nothing more. And they won't replace astronomers for now. So we will be able to do more science and more interesting science and not classify hundreds of objects every day by hand. So this is good for us. Trust me. And nowadays, the best algorithm is the random forest, proposed in 2001, and for the past 6-7 years is the best one. So it is really useful because it works with features like periods, amplitudes, and whatever. So there are available feature extraction libraries which do the work. So all is easy. But features are expensive. Computing periods is expensive. So we have to avoid that in order to be able to tackle the tsunami every day. So we have to get creative. So in order to analyze light curves, we have to fulfill a couple of requirements. First, the preprocessing has to be minimal, right? We cannot waste computer resources in the preprocessing step. We have to get to the solution as fast as possible. So our preprocessing must be efficient, must be fast, and has to be able to work with small data requests to a server. So if we want to classify millions of objects, we cannot ask for millions of light curves every day, every minute, every hour. So this is our constraint. So we designed a really simple preprocessing step, which is computing the differences in a light curve, point by point. So in this really pretty light curve, we take the first 2 points and compute the differences and do it for all the sequence. And then we do it again, but with a sliding window. Okay, so the width of the window and the size of the step are parameters that we specify later. But the thing is that we're able to take the light curve and doing just this. So we shift one space and make the subtraction. And then we sample the points and put them in a new representation of the light curve. Which means that in order to update or create or include new data points, we only need the last points of the light curve. So that's good. Then, what does this even mean? So if we plot this representation here, we get something like this. The delta magnitude and the logarithmic log of the delta of the time difference. And we have something like this. And the green points are all the light curves, are all the points. And the red points are correspond to one window that we sampled here. So you can see that every survey will have a specific cadence, and it will be shown here. So with this new representation, we can do things, right? So we prefer to build a machine learning model. And the other two requirements has to be that the model has to be incremental. We cannot compute everything all the time. We have to be able to update the representation, and it has to be able to work with millions of sources every day. So it will be cheap to run. That's important. So we will ask help of deep learning, which is really talk nowadays, but deep learning is really a hierarchical compositional model. Hierarchical means that you have feature computation step by step. So an advanced representation will be based on previous representations. Compositional will mix the information. So that's it. It's not magic. It's a model. Matrix multiplication. They are really hard to interpret, but these are tools. So if they work, we accept them. That's the point. So we use recurrent neural networks, which were developed to analyze text. So text is a series of characters, light curves are a series of measurements. So they are designing for sequential data. They create their own representation of the data, which is useful, and they can be updated as new information arrives, and can be trained with time series of different length. So they fulfill all of our requirements. All good? Questions? So we use a more advanced type of recurrent neural network. Don't pay attention to the inner workings, but pay attention to the three circles. We have the H, the representation, X is the data. So we take the representation computed in the previous step, we update it with the new information, and we obtain the representation that corresponds to this time. So we then build a model, which is really simple in terms of deep learning. So it takes each row of our matrix representation and then compute a classification score, which we can use. And that's it. So have to test it and see how it performs. So in order to test any model, we have to have databases. And we don't have many available. So we have Ogle, all of you are familiar with it, and which is really massive. And if we train our model, and Gaia, right? These are pretty different light curves, but we will use them to test the same model in both surveys. And these are the results. Don't pay attention to the numbers in the confusion matrix, but pay attention in the diagonal, and specifically the black boxes marks the classes. So we have error lyras, eclipsing binaries, long period variables, and so on. So we didn't tell the network anything about the relationship between our ABs and Cs. So the network learned by itself. So it's learning. And if we see Gaia, we see the same thing. It is not the best, but it's something. And one problem, we have to go ugly. Okay, we cannot work on pretty light curves. So we have to work with unbiased data, right? We cannot work with high signal to noise light curves. We need granularity. We have to be able to classify multiple classes and subclasses. The database needs to be large because we are working with many, many stars. We cannot work with small subsamples. And the data must be noisy because in any future survey, we will have noisy light curves. So we cannot sit happy with our model that works well and
so you don't like good data?
No.
Excellent.
So we will test our model in WISE. So we perform a cross match, a really rough one between with the Ogle data and Gaia data, and obtain like 120,000 stars with labels and periods computed in any of those surveys. And the results are not quite pretty, but the network still learns. So we have all the LPVs here, and we have no other confusion with any other classes. We have our lyras over here, which is good. The scutis are getting confused here, but also pay attention to the eclipsing binaries, non-contact, and Cepheids. Our method was able to classify those two classes from the noise, which are non-variable stars. So if we want to find micro-lancing events, we have to look all the stars all the time. We cannot try to compute periods. So this is good, but we can see how it performs in mean magnitude. So the random forest is really effective at where most of the objects are, so mean magnitude 12 to 13. But then if we go deeper, our model is able to recover more of the stuff. And that's not all of it, because if we look at the times that our model took to preprocess and train all the data, we see that the random forest in only took a week. And the training goes really fast, 10 minutes, 9 minutes, but it's still really large. Our model took 5 minutes to process 350,000 light curves with a consumer computer, like 4 cores, 8 threads. And in Gaussian-wise, it's not as impressive, but we still have speedups. So we are able to do it for millions of light curves really, really easily, and perform even better than the random forest in some cases. So that's all good, but what about VVV? So this is not pretty. This is really ugly. But at the time I trained with aperture photometry, which was publicly available. I didn't have access to the PSF photometry. The cross-match was really rough. We have no LPDs, they are all saturated, no self-aids. So we need more labeled objects. But if we retrain it and include more astronomical knowledge in the model, we can improve it. This is the baseline. We see that WISE works really well. VVV should be better, should be, and must be. And so the conclusions are that we are fast. We are able to classify without any feature whatsoever. We are really close to the light curve itself, which is really nice. And we can process millions in minutes. If we have access to a cluster, we can process the entire VVV really, really easily, comparing to computing periods for everything. And we have a room to improve. Better photometry, less dumb AI. This is really important because we didn't impose any conditions, any knowledge, any previous knowledge. So if we impose it to the network, if we ask the relevant questions, we can have answers. So the role of the computer science community working with astronomers is that we are working with really nice tools, but we need questions and we need to be asked specific questions. Like, I'm looking for microlensing events like this. So can you give me data? Yes or no? Can you simulate data? Yes or no? And that's it. We are a really big community competing in a friendly way to obtain really nice models that perform really well. And we only need a specific question. So it's your turn to ask us and to explicitly ask us, okay, we need this, we need that. Not like we want to classify everything. I'm looking for RRABs in this part. So we can fine tune our models and give you the results you need to do your science, which is the final objective. So, thank you.
Questions? Plenty of time. Just a comment.
I mean, do you think is your model able to incorporate additional data that's not light curves? I mean,
Yes.
you can, because often, the astronomical knowledge is about the colors and the locations and that kind of information, which obviously helps.
Yes, it is able.
Yeah. Okay. Good.
We have models that is working in multi-band scenario and incorporating frequencies and colors and all of that.
Okay.
I have one. It's like a comment, a question. Okay, you show us what seems to be a very powerful and useful tool for surveys like VVV and perhaps LSST and whatever. From your point of view, what would you need to keep going on your job, and how dependent on you will be this project? I mean, are you sure that you continue? I'm asking you this question because we talk about it a bit, and it seems to me that this is too important to be just.
It will be open to the community,
Okay.
and I did it like try to program it with following all the accepted practices. So you have a reprocess class, so you put your data, so like which class your star is, where is the file, and that's it. So you put all the list, and then you have a really fit method and a predict method. So it will be open to the community, and I want to maintain this because it's my baby. So I want to see it applied to real science. I don't want to test it on small databases. I want to do it on all the VVV. I want to look for weird things. So I want to.
Perhaps you would need a couple of postdocs working with you or collaborators to move fast in this direction.
I need
because you tell us that you need questions. So you have this machine ready to work, but you don't have the asset input from.
Right. So I need, if someone wants to find any specific type of object, and they say, oh, I have simulations, right, bring it over. Oh, I have observations, okay, bring it over. As much as you possibly can. And we can put it in the machine, and it will work because it is able to detect the patterns, and we have to extract them from the noise. That's the main idea.
Okay. It's unsupervised in that sense.
Right. The representation of the data is not as unsupervised as a clustering method, because we are saying, okay, this class has this representation. The network learns with respect of the class.
Okay.
But it will be nicer to add more astrophysical information.
Right. Yeah, that's good.
We have a question for our colleagues from other places.
From Cambridge.
I have a stupid question. so because I'm more interested in something that we don't know, like the ones presented by Roberto or presented by Lee. So is there an easy way? Because you say we need to ask the question that I want to know this class, right? But those weird thing, we don't have a class. Is there an easy way we can identify them from the others?
Yes, because there are works that learn how any classifier classifies things.
Yeah.
And based on the scores, it can infer some outlier score. But the novelty detection is a really hard problem that is even more advanced than this one. So the way I see things is that we need to classify all the simple things first,
sure.
and then leave a sample that we can analyze even further with more detail.
Yeah.
Where did this weirdo things go into the groups, like numerable, or is it sorted in another separate group?
I haven't looked for them. I could. If you have the wise idea, I can look for it, but it depends on the.
I mean, you need extra information because, particularly in the infrared, one of the problems is that there's an awful lot of things that you would think were weird if you didn't know they were young stellar objects because they're in a star-forming region, because they look really weird. But you're fairly safe if you say it's got an infrared excess, it's in a star-forming region, so I don't need to think too much about that.
Yeah.
And there's a relatively small number of genuinely weird things which are, isolated.
Yeah.
Yeah.
I have one, probably a very stupid question for you. I'm sorry about that. But have you thought about the use of ASAS, the ASAS survey?
Yes, but
They have a very interesting library of variable objects since, I don't know,
I thought so, but
it's really big, yeah? In the optical,
how many classes? That's the important question.
I would say more than 10.
Yeah, so there are different ones. So I think you're talking about ASAS, but there's also assessing.
Yeah.
So looking at supernova. So they are different data sets.
But they have cepheidas, they have
Yes,
eclipse
yes.
binaries
Yes,
of all
exactly.
kind. They have a catalog.
Yeah, but I haven't.
I don't know to
either. I have to.
Dante, what?
Very interesting. But one of the things that nobody's doing is VVVX. And we have 25 epochs. And just look for RLR in these new areas. It's new science. But because VVV, people have looked for RLR minors and things. So it's getting pretty confusing. But in the VVVX area, it expands. I don't know. If I were you, I would do that.
Yeah, I wanted to, but at the time I didn't have the PSF photometry. And as I wanted to validate my model, I had to use publicly available data.
Of course. Yeah.
But my intentions are 100% to analyze the entire VVV. So
Right, but this 20,
add X.
nobody's doing that. Nobody's looking at the 25 epochs that are already there in the VVVX. So this is a big niche.